So I'd like to introduce now our first speaker, Marek Drozdel, if he needs introduction in this forum. But Marek is a partner in Bayesian Fusion and also a Professor Emeritus in the School of Computing and Information, University of Pittsburgh, USA. He received his MS degrees in Computer Science in '85, Electrical Engineering '87, and Delft University of Technology in the Netherlands, and his PhD from Carnegie Mellon University. His research interests include probabilistic decision theoretic methods in decision support systems and human aspects of decision support. Genie and Smile were originally developed at the University of Pittsburgh. And I just add that Marek has been extremely generous over time, particularly with new starters. So I'd like to welcome Marek, and over to you, Marek.
So the time is running, so I'm going to start right away. I'm going to talk about a new addition to our offering that is called QGenie, Q for qualitative. And as I will try to tell you, it's a link between qualitative and quantitative Bayesian networks. There's going to be just one slide on Bayesian networks, and then a brief, really very brief review on abstractions of Bayesian networks. The rest is going to be about QGenie. Really not many slides, but hopefully a short presentation so that you can see what it is doing and what it is useful for. This is the promised one slide on Bayesian networks. It's essentially, what I wanted to say here is that the structure is usually given a causal interpretation, and it is not terribly easy to build, but between the structure and the parameters, the structure is actually considered to be easier to build, to obtain from experts. Of course, they are wonderful in terms of savings that they bring in representation, that there are many arcs, but there are many arcs missing, 123 arcs in this network and 2,400 arcs missing, which are the independencies that this model is modeling, capturing. There was interest in qualitative abstractions of probabilistic models. There is an attempt to bring kappa calculus to Bayesian networks by Moises Goldschmidt and Yuda Perl in '92. Kappa calculus essentially is an order of magnitude calculus. So they would put, instead of the number in the probability tables, they would put just the exponent, the order of magnitude. It was extended by Darvish and Goldsmith and other people. There are some follow-up papers. There are qualitative probabilistic networks by Mike Wellman, his dissertation work. There were several people who worked on them later. My contribution there was with my advisor. We extended the notion of product synergy and also proposed an algorithm, efficient algorithm for QPNs. But there were other people who worked on that afterwards. There's also work by Peter Lucas on patterns in qualitative probabilistic networks, where he interpreted existing constructs like canonical gates in terms of qualitative patterns. Interestingly, while this work, of course, was touching on knowledge engineering, most of it came from the worry that probabilistic inference is NP-hard worst case, so qualitative schemes should be faster. The problem with inference in qualitative schemes, the QPNs, they're really weak. They operate on signs. The problem is that suppose you, in this simple network, you observe a low oil level in the car, and then want to calculate the impact of observing blue exhaust from the car. So you essentially get this plus sign and want to propagate it through the network. You propagate it, and in addition to the positive signs of the links in this network, they're all positive, you get negative synergies between the parents of the observed node. So multiple paths that are reaching some of the nodes are of conflicting sign. And this is really very typical for QPNs. Any sizable network will have a lot of question marks, which means you can't resolve that using a purely qualitative scheme. There was some work on improving that by the group of Linda van der Haag in the Netherlands, but still, I think the problem remains. Most queries result in undetermined signs. I wanted to make 2 points about Bayesian networks. The first point is that precision of parameters doesn't seem to be crucial. There's a series of papers that I published with my wife, Agnieszka Oniśko, and this study may be interesting to you. What we did is we tried to round all the parameters to several values. So let's look at this one. We rounded it to 5 intervals. This is a scatter plot. So x-axis has the original parameters. The y-axis are the transform parameters. So let's say a 0.4 would become a 0.4, but 0.3 would become sometimes 0.2, sometimes 0.4. Why sometimes this, sometimes that? It has to do with rounding proportions. It's a troublesome thing, and proportions have to add up to 1. So there are some algorithms that, some tricks that are done here. In any case, progressive rounding, 10 intervals, 5, 2, 1. What happened to the accuracy of a network? We actually studied several networks. This is for HEPR2. This is the original accuracy, actual accuracy when rounding to 100 intervals, but it's very close to the original accuracy of the model. As you continue with rounding 10 intervals through 5 and 3 and 2 and 1 interval, the accuracy decreases, but not as much as you would expect it to decrease. Of course, you need to make sure that you don't introduce zeros by rounding. As you know, zeros are a very, very troublesome. 0 is a troublesome number in Bayesian inference. Once 0, never anything again. So we replaced the zeros by epsilon, 1 minus epsilon. So this rounding to just 2 values means to epsilon 1 minus epsilon. Such a terribly rough rounding still leads to loss of accuracy of less than 20%. So that's an interesting thing. It kind of confirmed the general feeling in the community that numbers are not terribly important. The second point I want to make is that computational complexity of Bayesian networks, it doesn't seem to be a showstopper in practice. Here's one of the networks that was developed by our users. It is a model for diagnosing diesel locomotives, 2100 nodes. Updating this network, of course, it depends on the number of connections and the topology, but in this network, the update takes a fraction of a second. So I know SMILE is fast, but still, probably most packages will be able to handle networks of that complexity. And developing a network like this will take probably months, if not years. So the 2 points, numbers are not that important, it seems. And the second is that the speed of inference, it's not a big advantage of qualitative schemes. So to sum up these observations, precision is not crucial. Computational complexity is not a terrible problem. Knowledge engineering is still a problem. Of course, we have canonical gates that can reduce the number of parameters, but still it is a problem. So starting from these observations, the question is, why not just provide a qualitative interface to an otherwise quantitative network? And that's exactly what QGenie is, qualitative Genie. It has SMILE inside, but a qualitative interface. I'll give you a brief demo at the end of the talk, but just a few more words. The building blocks is the Morgan gate. It was proposed quite a number of years ago by my student and myself. It is a combination of noisy AND, noisy OR, and negation. You have 4 types of interactions, and as you know from logic, AND and negation is enough to represent any logical function, so is OR and negation. We keep OR and AND because it's conceptually easier for the users. The interactions can be of different types, four types here in the Morgan gate. A cause is like in a noisy ore. Pneumonia makes fever more likely. Flu, the same. Barrier is it's a cause that acts the other way, so it's a negative influence. Really far-fetched bodily temperature balance makes fever less likely. Being alive is a necessary condition, a requirement. You need to be alive for fever to happen. And aspirin, Tylenol are inhibitors. Essentially, aspirin, Tylenol, and being alive act as end inputs. So if you take aspirin, no matter what causes you have of fever, no matter how high it was because of this, is going down with aspirin intake. This is the building block, and with this building block, we can construct models quickly. So it is all, nodes are propositional, true, false. Interactions are one of those four types. And parameters are, there's one parameter for every node, and there's one parameter for every arc. So we hide the numbers from the user and operate on rough order of magnitude estimates that are inputted by sliders. Few parameters. With complex domains, you can construct these models quite quickly. Get the structure and then a rough order of magnitude numbers. Two applications of that. It's a good starting point for quantification, and it's also useful for group decision-making sessions. I'm going to show one slide on each, but actually we should move to the software. So you develop a model in QGenie and then export it to Genie, at which point you have a fully quantified model, which you can elaborate on later. And the group decision-making sessions essentially is constructing a model very quickly. Often you can do it in a few hours before the meeting. If it's a complex model, maybe you spend a day on it, and then project it on the screen, and there is a focus to talk about rather than suspicion that we are talking about the same thing, possibly talking in parallel, etc. If there is something wrong with the model, somebody raises that point, you can change the model very quickly, and you get immediate answer to what-if questions, the instant gratification. Very good. So this is really the last slide. I'll show you QGenie live. Before I stop for questions, let me get a model from repo, from the base box. Here's one. I constructed it very quickly before a presentation at a major airplane manufacturer. I wanted to make a story. So the story is that you are building airplanes. Somebody ordered the airplanes from you. You're interested in profits and future contracts. The numbers, as I said, if you double click on any of the arcs, you get the strength that the arc has. It's also shown by colors. You see a darker red is 80%. The coloring scheme can be set. You set for 0 and 100, and then you can test various ways of kind of changing that thing. There's one number per node also. It's prior belief if there are no parents, and leak if there are parents. Leak has a similar meaning in the Morgan as it is in noisy ore. So a few parameters. What can you do with this? You can observe things. Let's say the client comes back to you and asks the airplane to carry more. You see how that thing propagates through the network. You see colors changing. What if the client asks for higher speed requirements? You see things are changing. The profits are still in the green. You could also calculate. Oops, I cannot see. This thing is.
1 minute, Marek.
Okay, so I'll hurry. I'll finish, no problem. So there is a special window where you can ask what are the most effective manipulations in order, of course, to influence our focus, which you mark. You can do, this is a real model, this one. It was constructed in the military environment, Naval War College, a stability model for a region on the Earth. The idea is that you want to keep the region stable rather than sending soldiers to fix problems later. Submodels, all of it is qualitative, and here also you have manipulations and observations most effective. You can do the same with dynamic base nets. So you can see how things are changing. You see the gradient of change. You can view it as temporal beliefs also over time. So the underlying thing is quantitative. The interface is qualitative. Whenever you want to add an arc, the last thing, I didn't show you that. When you add an arc, the question is which type of interaction it is. Once you pick it, you can go there and change the weight. That's it. I wanted to finish on time so that we have time, a few minutes for questions. Very good. So thank you.
Thank you very much, Marek. And yes, I've just got to say that we found it very useful to explore qualitative Bayes in advanced applications, certainly as a start to projects and as unifying diverse expertise. Anyway, I'd like to hand over to our moderator. Do we have any questions, Anka?
Yes, we do. We have a question from Bruce, who asks, can you run QGenie models backwards by specifying desired outcome states and seeing what would most likely lead to that outcome?
You mean like observing something backwards, like negative profit? Yeah, that's what you mean, right, Bruce? It's the typical Bayesian network stuff, right? So we can observe anything anywhere and see what could have caused that.
Thank you.
Is
yes.
this what you would like to do? Yeah, these are Bayesian networks.
Okay. Thank you.
I didn't show you the exporting. You just export it to Genie. And then you can open it in Genie. You have a quantitative model where you can see the full definitions. Okay.
We have another question from Penny. And the question is, what are the different colors indicating?
Okay, the different colors. The colors of the nodes. I should have said it. I practiced and I was preparing. The colors indicate the marginal probabilities. Essentially, you define them, the sliders. This is what represents 0 probability. This is what represents 100% probability. And for any node, you can reverse that. If you think that 0 is bad, you just reverse it. So it's the posterior. Essentially, the idea is in a group decision-making session, you want the model to indicate where the problems are. What is the troublesome thing? And that's the idea of coloring.
Thank you. Sarah would like to know if QGenie work with nodes with multiple states?
Unfortunately not. That's a limitation of the Morgan gate. We don't have a good, like noisy OR can be extended to noisy max. We don't have that for the Morgan. So no.
We have time for one more question if there is, Anka.
Okay. Yeah, there's a couple more. Anne-Marie would like to maybe have a bit of an explanation about what's the theory behind the calculation of setting the arcs.
Okay, that's actually that's really the Morgan gate. What is the meaning? That's probably the question, not the calculation. The calculations is like a noisy OR. You have the meaning. You can translate it to any conditional probability table. We do the same with the Morgan. What is the meaning of each of the different arcs? It's the very simple thing I try to present, but there are fine intricacies here, probably beyond just a couple of minutes answer. Essentially, positive and negative influences that are working as or and and. But the online help has a good, thorough explanation. I hope.
I don't know if you will still be able to join us until the end of the session, but in the break, I'm making breakout rooms, and I'm gonna associate you with one particular breakout rooms, and people can come and ask you questions if they still have some. So if
Yes,
it's
I
not
will
too
stay.
late for you.
I will stay up. I'm very interested in the other talks.
That is wonderful. Thank you, Marek.
Okay. Thank you very much, Marek. Anka, can you confirm whether we have Anders online?
I believe we don't, but
Okay.
Anders, if you're here,
Please let us know.
Yeah.
All right. I'm going to assume Anders isn't there. So our next talk will be Dr. Tang Kao. And Tang is a mathematical modeling research specialist in land capability analysis branch within Defence Science and Technology Group. He has been leading. He's been a leading force in the application of Bayesian network modeling to defence, and particularly Army problems, and has been key in the development of mathematical modeling as a capability within land capability analysis branch. And apologies in advance that that was a deviation from what you gave me, Tang. But I'd like to welcome Tang, and Tang is talking today about Bayesian network modeling for military utility assessment of direct energy weapons within future tactical land warfare. Over to you, Tang, please. Tang, I can see your screen. I can't hear you at this stage. Tang?
Yeah, so
Okay.
you can hear me, can see?
I can hear and see. Over to you.
Yeah, thank you very much, Andrew. This is the work we do to evaluate the new technology for the Army. So military utility, it means what we do the Army gain when they apply the new technology. So the work of collaboration between the S&D group and Bayesian intelligence, especially Stephen Mascaro, so with the great help, Stephen. And I would like to highlight this work has been presented in October to the U.S. Army Operation Research Symposium, but I think it's useful to share with the community around here. That's why I present it again. So I will go in quick because it can be a little bit long. At first, I highlight a bit, why we do this work. This work is a part of the task in DST group. We call it future technology concept evaluation. So when we look at the future technology, we talk about 20-year time frame. So it means that it's still not certain how to use it. There's the potential in technology, not much data available, a lot in idea, potential, and how to use it. So that's why we call it concept. So there is a lot of way, and because just understand technology is one thing, but how to use it in the military operation is a different thing. So there are a lot of work to structure it. Most of the time we use a kind of called disrupt technology war game structure to explore the concept. And after we propose a number of concepts and we need to evaluate them, so there are always two parts. We design the concept to use the new technology and then to evaluate them. And how useful it is, normally it's called the military utility. The term utility linked closely with the Bayesian network, so that's why it will come later. So one of the technology we work in here is the direct energy weapon technology. So it means that we have two technology we explore around here. One is high energy laser, and another one is high power radio frequency. And how to use them. So those two technology mostly to disrupt the electronic and communication system. Laser can have some physical harm. It can drill through some vehicle armor, but it takes time. So it means there are different way and different range and different environment. So it's fairly complex when we use it in military operation. So there the initial some series of workshops use the disruptive technology war game. to design the concept and qualitative assessment to take a survey which one is more useful. And so that is the first part. Understand the technology and design the concept. So you can look like this. So I mean there's the understand of now I call the HPRF. It means high power radio frequency and laser, the HEL. So you can see it can replace some the artillery, but to put it in, so it depends the range. So you can see it, there's a line on the right side is the enemy, and on the left side is technology. So try to use it. It depends on range. So depend on just what type of enemy equipment in there. So that is the concept to use. So how you deploy, how you combine, how to use them together. So that overall, it means the combat team, it means the size of your army about few hundred people. So I mean, this is and it's short list to around 11 technology. You can see some very small, some put in the unarmed vehicle, and then some medium. And most of medium and heavy, it means it sit on the vehicle, so very heavy and very power consumption. I'm not going into detail of this one because it will take a lot of time. The main purpose of this one of this is about methodology. And I would like to put in the disclaimer because all of this one is always secret document. So all thing I present in here is just for the common knowledge only. So I mean nothing sensitive talking around here. So all your ranking in here artificial doesn't mean it is a real ranking. So I mean the main talk around here and the main work, I mean our team working around it to look for the methodology. What is the set of methodology should we use to do this type of work? How to evaluate the concept of the new technology. So I mean at first we're looking at how to evaluate them. Secondly, how to rank them, so how to prioritize them. So for your defense to invest on that. And what is the best way? Because one is different, but how to combine them, and what is the optimal way to combine them it's a very, very tricky. And so there are three research questions. So the first one is Bayesian network and utility model is a suitable one to do it because most of technology don't have much data, so not very high uncertainty in there, and it rely a lot on expert knowledge. So Bayesian network is a suitable tool, and combined with utility because we got multiple utility, multiple things in there. So make it Bayesian decision network is suitable to do that one. So to address the research question one. The second one is we have to rely because from time to time you can Bayesian network explore a lot of possibilities space. So not always possible to use Bayesian network alone. So from time to time, you got multiple utility, and you have to apply some method like multi-criteria decision analysis to combine them and to make a ranking. So that is address how to rank a research question two. And the third one is how to make it all the best combination between them, how to search for optimal one. And we use it, normally we use multi-objective optimization. Most of the time heuristic because classical one is not quite applicable in here because the size too big. So that is the method we do. So this is I go through very quick about the analytical framework. I mean, at first we have to define what is utility in here. Normally, most of the time, utility is can army survive the mission or can they achieve the mission and something like that. So that is the, and the concept map, it means how to link the causal map, how to link between them and the way we use and different tasks and different environment. There's a lot of dependency in here. So how we structure and how we elicit the probability, and we tend to more to apply the Delphi to combine between the multiple expert input to reduce the bias. And then we get the utility and we aggregate by MCDA, and then we use a multi-objective heuristic algorithm to search for the best combination. So you can look at first the structure is we need to get the abstract. So we got the DW option. When you look at the top line, we got the DW option. There are 11 in here. And there the cost, so roll down the down where we resort a very high energy user that carry a lot of fuel and power around. And it can have discrimination because when you pump in the high frequency radio, high power radio, it can discriminate, it can disrupt your whole communication from output and friendly force too. So it got a cost. then it can gain a lot. So I mean, at first we apply in and we can do it some damage to the rat capability. And when we can do something for the rat and then can affect the rat team, can achieve some outgo and achieve the task. So when we roll down to the detail, you can see the blue box is the utility, so you can find five utility we talk in here, discrimination. So it means the measure, it means how it does discriminate the civilian and the outforce. And operational cost, being it affect your fuel and everything you carry in battlefield, how to guard the equipment and the survivability and ability, I mean the measure of the ability of our force to survive and mission success, the ability of our force to achieve the mission. So you can see that is a five utility in there. So that multi-objective we have to deal with five, and it's not possible to do Bayesian network to combine all of them because all of them got distinctive value. So it needs to you apply some of the MCDA technique to do with that. So at first, now I go a little bit in here, and this is a packet based on intelligence providers, a great tool to help. At first, we try to deploy the Bayesian Delphi, but unfortunately, Bayesian Delphi is online, and our network is the defense network. It got a lot of security restriction in there, so I mean we stripped down that one, and you a lot of spreadsheet from and visualization tool from Stephen. So we send out the survey and capture the data. What is the impact on its technology to different type of the enemy like dismount and tank and aviation and artillery. And after that, after we got all the survey back in the first round, we roll out, we visualize, you can see if the thicker line, it means depend on the line, how many people got that opinion. And then the second round, mean consolidate by get everyone in and confirm the network structure. And the next one is one we got the network structure confirmed and still apply the Delphi, the spreadsheet. But because the number of the size CPT is very large, so we apply the interpolation approach proposed by Ken. So look at and worst best and then interpolate anything in between. So I mean that the way we significantly reduce the size CPT. So that is the approach. I mean, in the discussion, we can discuss because elicitation is always a bigger part. And there are always two parts of elicitation is how to aggregate between the multiple experts and how to reduce the size. That always that like Marek touched by about that qualitative and things like that. And how much accuracy we lose around that one. I think that's the topic I mean, would like to discuss in the discussion panel. And now it did how your network look like, finalize after we do a study. So in here, we drop down the discrimination and everything negative. We do it for trade-off later on, but first you can see it controlled by multiple tasks. In here, it got A tasks, and it got different terrain. And so it means all that those one combined, and it will affect between all your DW option and go into your your single platform, and then go to the team and it got the coach, because if you use the technology, it expose your force to your red force to know where you are, because it got very high signature. So in the end, you can get all of that calculation, that the probability your force to survive and probability to achieve the mission. Yeah. And this is the
Tang, 2 minutes.
yeah, so I will go through quick in here. So at first, so you can see in here, I mean, that is a quick ranking about it effect on the task and how it achieved, how it survived. So you can see overall, I mean, around medium range, it tend to achieve the best around here. Because here it can be very, it got a lot of negative thing because expose the signature. So you can see it. And now we expanded one to bring out more utilities, or bring in the resource operational cost and discrimination. And so I mean this one got the trade-off because achieve can got a big effect, but it also got a big discrimination, and it also got it very resource intensity. So in the end, you can see it how we search for the optimal. So then number, you can see around A is the best. It's not always best to bring in the A. After A technology, you combine together, you can't get it any better. But this without trade-off, if we bring in trade-off, you can see it only it dropped very significant. So combination of 60 around it where you don't achieve a lot more because the heavier one. Some medium heavy one got so much discrimination and so much resource intensive, so it dropped down. So that one. And this is the method we use. We combine multi-objective optimization where we search for Pareto front. So we got about over 2 million combinations. We reduce to 5 solutions only. And we don't apply any reference weight aggregation. And so it means this way, because from time to time, I mean, because every decision maker, they refer weight, they give in the weight. But that's not always the ideal. So this is the alternative one, is to search for the non-dominant solution, use the Pareto front. So I mean, from 2 million, we read down to 5 solutions only. So only need to make decision around that 5 solution. So that is all, I think. So that is the conclusion.
Only place I can use Zoom to run a conference from.
The only conclusion, that is a good tool. So I mean that is a lot of progress we make around this one. So I mean the combination, we use the Bayesian network to evaluate utility. We use NCDA to aggregate that, and multi-objective optimization to search for the best combination and provide decision support tool. So that is all for me. So quite open for the question.
Thanks,
Okay.
Tang. Much appreciated. And I'll hand over now to Anko with any questions.
Yep, thank you. There's a question from Bruce about the interpolation. Was the interpolation of the CPT values a strictly linear interpolation? That's the first question. And then have you considered needs for nonlinear or non-monotonic interpolations? And the third question, are there any apps for this?
Number one, interpolation is linear. That we would like to improve, but because this is a proof of concept, so we don't go into that lengthy one, because the technology we haven't got mature enough to make a real assessment. This is to test whether the methodology is working or not. So it's no point to go to more precision of your one, but certainly we will explore the different type combination, including the applied beta distribution from Bayesian intelligence, and Anka also do some work in that. So there are different ways to do it. Also, we got the best and worst and to distribute around. So we will explore and include in noisy or noisy marker or something. So it's got different ways to combine that. So that certainly we'll do it when it comes to the real evaluation to advise me which one is prioritize that. And can you repeat the third one?
Are there any apps for that?
Any apps?
Any applications that you can use? I suppose that's a question more for Stephen.
Application, I think it's that application you mean it to evaluate, is it? Is that what is useful of this study, is that right?
Maybe Bruce can clarify the question.
Yeah. Wondering if there are any applications for doing non-linear or non-monotonic interpolation.
That one probably for Steve. I think it's quite likely the beta distribution from between elicitor, is that right, Stephen?
Yeah, that's right. So Interbeta supports, well, certainly it supports non-monotonicity, and it supports non-linearity basically in a slightly different way, but you can incorporate a lot of that non-linearity yeah, in different ways. Not everything supported, but quite a few different approaches to non-linearity. And that's in the Interbeta tool, which is online and public, and I can possibly paste in a link for people to.
That'd be wonderful.
Yeah. Cool.
Thank you much. Thank you.
I should also mention that the parameterizations we did for this particular project, we actually manually included synergy in some of those. So we basically did just a linear interpolation initially, just with Kane's interpolator. And then we did adjust. We said, okay, has this moved, far enough down, given that we've got multiple combinations, and if it wasn't far enough, then we'd move it further down.
Yeah, thank you. Look, we got time for one more question, Anka.
Then I have a question.
You
mentioned. Do you want to go for yours? It's fine.
No, it's all right. It's okay.
You've mentioned that you used something that you called Bayesian Delphi, and you went back and forth with Excel spreadsheets and Stephen. Can you say a little bit more about what's Bayesian Delphi?
Bayesian Delphi is an online software tool developed by Bayesian Intelligence to create the kind of question you send out to the expert. They do independently, but it means that you got the facilitator, you control online, so it got the very correct interface. So I think that Bayesian Intelligence do have it online assessment. I think when you go in, I think later on some that relate to the BART. I mean that I'll talk a bit about later on, because I think BART do have some relationship with Bayesian Delphi. Mainly apply the Delphi approach with two routes, but they create a lot of the interface in here. So unfortunately, we can't deploy it, so we have to use the Excel. It's still in the end, and almost the same effect. It means you send out the spreadsheet, they do independent, because first round we never want to influence someone to like Brooks highlight a lot of issues with experts in the room, right? Where always someone more charismatic dominate the room and things like that. So the first round, I mean, we want the expert to be able to do it independently. But then the second round, he tried to smooth out what is a misunderstanding, to try to get something consensus. Some visualization tool developed by Stephen is very useful, so we move around up and down, and the value, and in the end, the stick at the one everyone agree that's sensible.
Thank you.
Thanks for that. Look, just on take prerogative to take a quick question,
Yeah.
Tang, and that is, do you think you could, if you had have had access to QGenie, or would that have been a potential candidate for getting this concept development up and running prior to a more formal model?
Yeah, I think it should be a great tool. I think I would like to get, I mean, the combined noisy or noisy MAC standard and beta elicitor, and then all your interpolation. So how your interaction with that one, and certainly would like to get some interaction with Marek later on. And can we, once we settle on the methodology, I mean, can we build in Genie to do something with that elicitation? So it should be done outside. It's okay to do outside, because probably if we go to the Genie, it can be made too heavy. But QGenie definitely it got a right. I do use QGenie from time to time, so I know it got the right interface. So very good to capture, and most of the Bayesian network relationship is still there. Just something about the dependency. It can be important. We might need to look a little bit more in detail, because a lot of independent, a lot of G2 assume a lot of independent assumption in there. So I mean, and dependency is a thing that makes the GPT grow very fast. So that is a thing that we need to look more careful into that.
Yep. Thanks very much, Tang. And we'll move on to our next speaker. And our next speaker is Ian Fitzpatrick. And Ian has 35 years of experience in the energy industry. He specializes in power engineering, risk, with particular attention to wildfire risk at Essential Energy in New South Wales. Ian's been a passionate contributor to helping industry address risk posed by power lines and ensure safer communities, which are very relevant given our previous summer. The most enjoyable part of his role in the interaction with fire researchers is the interaction with fire researchers and industry colleagues. Ian gained experience in city, metropolitan, rural-based companies located in Victoria and New South Wales. And I'll hand the floor over now to Ian, and I'll make sure you get the full allocated time. Ian, over to you.
Thank you, Andrew. Can you see my screen okay and hear me?
I can see your screen and I can hear you.
Great. So thanks for inviting me along, and the purpose of my talk is to give you an industry perspective in terms of how an electricity utility is using Bayes network to help solve a problem. So we invoked on a project with the Energy Networks Australia to try to come up with a solution to a problem that was nagging utilities across all of Australia. And I'll go to how we developed the solution to do that. The problem we were trying to solve is how to quantify the expense or the impact of bushfires, particularly big bushfires in Australia, to properly quantify them. The need for that was born out of the fact that we know that majority of power lines in Australia are overhead and they're exposed to the elements, and they do start fires, and they're particularly prone to starting very bad wildfires in particularly bad circumstances. And you would have seen that in some of the news after the Black Saturday fires in Australia, where a significant number of those fires were started by power line faults, and you've seen it repeated in California in recent years. The point I wanted to make about this slide was that both in 2017-18, we witnessed record-breaking economic losses from wildfires, over 20 billion, driven by the catastrophic ones in California that I mentioned. However, they're not likely to be all of the costs. They were really just counting insured losses for people, and we all know that when a fire occurs in a landscape, that the overall impact on communities is much wider than that. We also know that when the weather's really bad, the cause of fires from an electrical cause significantly rises. So under normal weather conditions, fires due to electrical causes are probably the lowest of all these typical ignition causes that you get in a landscape. But as soon as your wind speeds and your forest fire danger indexes are rising significantly, then those causes due to power lines rises quite significantly. We also know that looking at house losses, for example, from power line fires, that they're a significant feature again in terms of they may not be responsible for the most amount of area, but certainly figure very highly in the number of house losses from those type of fires. And that's probably because power lines tend to be where people are and where infrastructure is. So the industry need was to justify our expenditure on addressing this risk by properly understanding the cost and impact. So we went about doing that with a 4-phase approach, if you like. So the first phase was to understand what kind of data we would need to help understand how we're going to solve the problem and understand the quantitative evaluations. And then we used these 3 further phases as quite a novel approach, and we worked on linking 3 distinct pieces of work and integrating it into one specific model that would give us the outputs we needed. So we integrated a fire simulation tool with some economic modelling and the Bayesian network modelling, and I'll go into that in a bit more detail. What we wanted to do was test this method over a number of case study areas in the Australian landscape, and they're represented in that table on the left-hand side. So there were case studies, there were 8 case studies across 4 different states in Australia. And we did that for a number of reasons. One was to give some diversity in testing the model across different landscapes, but also those areas had very different economic dependencies for community. So we were able to try and test some of the economic impact on different areas that rely on different things. So, for example, Yass, Goulburn, Port Lincoln, or Mount Lofty ranges to some extent rely on agriculture to build their economies, their local economies, and a lot of agricultural assets, whereas some of those other areas relied heavily on tourism, such as the Blue Mountains, and others were significantly dependent on vineyards and viticulture. So to build these models, the data sets we were looking at across the study regions varied. We had to take weather from weather stations in those areas. We also had to look at the power lines that we had in those areas. So it was reliant on setting simulated fires along our power lines every kilometre, and under the fire simulation tool, looking at where those fires would end up. So as part of the data set, we ended up with, for example, a range of something in the order of 14,000 fires simulated in one region to 80,000 in another. And that was a product of how much weather data we had from the weather stations there, as well as the number of ignition points or the amount of infrastructure in those areas. So the fire simulation tool, for those that don't know, we used Phoenix fire risk modelling tool, or Rapid Fire, from University of Melbourne, and I notice Kate's on the line. So Kate was involved in building this work for us, as well as Trent Penman. And really, it's agnostic to what type of fire tool you use. In the end, you could use any sort of fire simulation tool, but we chose Phoenix in this particular case. The fire simulation tool was fundamentally driven by these four types of input. So the weather impacts, those ignition points, the fuel loads, and the assets occurring in that region. So we lit these simulated fires, and then we stressed them under certain weather conditions, really bad fire weather conditions, to see where those fires would end up, so that we had a proper understanding of what was impacted economically. The second part of the project was to incorporate the economic modelling, and we used Veronique Floric from University of Western Australia to help us with this problem. Her particular expertise is pricing the cost of natural disasters, and there are specific economic tools that you have to use for pricing different elements. So we broke this into four distinct parts. There are direct and tangible things that are affected by a fire. There are things that are impacted by a fire directly but are intangible to cost. And there are indirect consequences of the fire that are tangible to cost. And then you have the indirect impact of fire and intangible to cost. So this quadrant here would be the most difficult to actually cost. And for the purpose of testing the method and proving it, we focused on the direct tangible, and we did include lives lost from the intangible, because we had methods for pricing that as well. The third element, once we had the economic modelling joined, if you like, to the fire simulator, was to use Bayesian networks to understand the probability of this particular event occurring in the landscape. And I must confess that up until I got involved in the project, I didn't know anything at all about Bayesian networks. So it's been a journey for me, and an interesting one. And I can see there's significant application beyond this particular project for the energy utility space, for things like understanding failure modes of our assets, understanding other public safety risk potential, understanding the risk of outages and loss of supply on communities and so on. This is really just an example of the table that was built. So we looked at the FDIs across the different forest fire danger options, from very low risk to extreme and catastrophic risk. We looked at the probability of a fire start from electrical assets under those same conditions, and then we measured, the size of those fires depending on what you're selecting here and looking at, and then the size of those fires to some extent drives the loss, which is shown down below in section 4. And that's the estimate of the impact probability from our assets that we're interested in. We're interested in two components of that: the individual loss of the individual components, but also the aggregate. That's just a bit further information on how we built the nodes and what they mean. So you can look at that. The result outputs we got from the modelling was in a couple of parts. There was a tabulature option to give you tables of losses. So this is an example. I think it's the Blue Mountains case study, for those that know that area. And it looked at the individual loss. We looked at an upper and a lower range, and then we had a mid-range in here. So these are the lower and the upper, and this is the mid-range. So there's about $91 million of monetised risk in losses due to fire in the Blue Mountains from the infrastructure in that area. And you can see it's quite dominated by cost of lives lost and cost of homes lost. So that was an interesting thing that we learnt in the modelling, that for many of the case studies that repeated itself, that really the cost of other types of infrastructure paled into some insignificance compared to these two. It wasn't always the case though. The second part of the output from the project was to get a spatial representation of these losses. And we did that in two parts. The spatial representation on the left is where the loss of homes, lives, or infrastructure, of other assets such as agriculture and so on occurred. So that's the actual location of the loss. But what we needed to understand as a utility was, well, which parts of our network cause that loss? So the second spatial output was the representation of our network. And you could click on, these are the poles on a particular power line and the black dots, and you could click on that and you could see the correlation between the loss from that area to the loss in the landscape of the actual assets. Another output we played with was a HDM tool, which is available online for use. And it gives you the radar plots that allow you to compare one case study or one region analysis to another. That was another important part for the utilities. In the past, we had tried to price the cost for building our investment cases to go to our energy regulator to get funding. And we used a cost that we applied over our entire network. What we know from this modelling is the costs vary significantly from one part of our state or network to another. So you can't treat it all the same to be more accurate. This allows us to break our areas into regions, do the cost analysis, and then come back and have a look at how some regions are more impacted by specific types of loss compared to others. So the applications within the industry, as I said, were to help quantify and justify our investment. One of the things we had to solve was we had to prove to the regulators that we were minimising safety risk to so far as reasonably practical principles.
Ian, 2 minutes.
Great. And to do that, we have our own value framework tools that we use to justify our investments and make sure those investments are spread proportionally and appropriately. So we use a number of different frameworks, and in this particular case, we're using a product called Copperleaf, where we put all our capital and operating cost projects into the pipeline. You set your parameters around the tolerability of the risk and the monetized consequence of those risks materializing, and it outputs the project. It lifts the projects that are most warranted to the top of the list. What I'll say about this is that gives you a very good quantified version of what you need to do, but looking at the UK oil and gas principles, you also then need to still overlay things like, well, regardless of whether it stacks up financially, there may be an imperative due to a code or standard or compliance requirement to do it, so you must do it. You also need to test when you're getting these kind of results, whether they still meet things like good industry practice, good engineering judgment, consistent with societal values and those kind of things. So whilst we've got this risk-based approach, you still need to consider these other things. So just in finishing up, the next steps for us in terms of the project method is to have the work peer reviewed, and the University of Melbourne's in the process of doing that. To roll it out nationally within the industry, and we've already had an uptake by the members of the Energy Networks Australia, which are representatives of all utilities, and they were hoping to run a national conference last year to roll out the work, but COVID put a stop to that, so it's likely to be in the new year. And we'll, like I said earlier, what we've learned from this is Bayesian networks is really an ideal product for us to use for other risk cases and for other failure probabilities and impact. And finally, that it just gives you an indication of the research team that worked on the project. So on the right-hand side here, these are the industry representatives primarily, and we work collaboratively with the researchers that are the experts in the economic modelling and the fire risk modelling and the Bayesian network approach. And it's a model now for how we do other projects in the utility space, because this collaboration of experts and industry working together to solve problems we found works very well. That's all, Andrew.
Thank you very much, Ian. So Anchor, questions?
Sure, thanks, Ian. Anne-Marie asks, how is the cost of life quantified?
There's several developed methods for doing that. I'll just see if I can turn my screen share off. Yeah, so there's specific economic ways to do that, a statistical life loss, if you like. And I think it's currently running at around $4 million per life loss, but Kate, you can correct me if I'm wrong. It's something in that order.
4.8, I think, at the moment.
And it's the value of a statistical life. So it looks at the loss of losing somebody and what they might have provided economically as they went through their life, and they contributed to consumerism and working life and taxes and all that kind of stuff.
The next question is from Tang, and he wants to know if the BN learned, if the BN was learned from simulation, from simulated data.
I'll throw that one to Kate.
Sure. Yes, so part of it was learned from the simulation data. So we ran a whole lot of different simulations, and we linked single fire runs, and we linked that with a whole lot of different weather as well. So we ran it under all of the different weather FFDI categories from low to catastrophic. So that information we extract from our Phoenix fire simulations and then use that to populate the top level nodes, so our fire danger rating and also the probability of ignitions. So we do use the actual output data from the simulations in the top level of the basenet.
Yeah, thank you. So you got multiple simulations and you link them together, and so I mean, is there any issue to create a context and assumption to link them together, or you have to enlarge a model and use your expert to help to link them together?
So we average we generally take an average from the simulations per FFDI category. And then at the other end of it, we rerun individual locations to spatialize the basenet. So it's sort of, at the top level, we take an average and use that average value to fill the top FFDI node from the simulations. And then at the other end, when we spatialize it, that's looking at individual ignition points. So that at the other end, it's not aggregated.
Yes.
Does that make sense?
Yep, makes sense. I'm quite interested because I also do some learn from simulation, so I share the same interest. That's why I came to ask the question.
Sure.
Inka, we've still got time for about 2 questions.
There's no more questions in the chat.
Then I'd like to. Oh, sorry, over to you.
Go. No, you go. This
All
time.
right. I was just going to simply ask Ian whether this, or is there any intent to apply this to some sort of predictive maintenance? So in other words, use the risk measures and the analysis to actually proactively get ahead of how you maintain the assets, the power network assets.
It's a very good question, Andrew, and the answer is yes. And in fact, one of our colleagues in WA, Western Power, are doing that, doing a lot of that at the moment. In the last year, at least the last couple of years, they've been on a journey with Bayes Networks to do a whole range of engineering functions within the business in understanding those kind of and using it for those kind of options.
Right, and are they giving you good feedback? I believe they've been using some method like that for some years, but are they still giving reasonable feedback on that?
To be honest, I haven't had a lot directly until I got involved in this project, and I started reaching out to them because I heard they were using it probably more regularly than any other utility in Australia.
Right.
And we're quite keen to understand and share the templates that they've built with it. And it's probably you know, a piece of work going forward. What we have done in my particular company in Essential is we hired a lady called Victoria Hogg, who works in our risk space, and Victoria used to work in Western Power, and she alerted it to the work that they're doing over there as well. So we'll reach out through Victoria's contacts to work more collaboratively with them to try and, yeah, learn from each other and not reinvent the wheel.
Thank you very much, Ian. Look, I think we've got to move on. Anko, there might be time later to ask your question.
Fine.
Thanks, Ian, and I'll ask you to stop sharing and I'll introduce our next speaker. So our next speaker... Sorry.
I have stopped. Yep.
Yep, okay, that's right. My problem there, Ian, not yours. So I'd like to introduce our next speaker, Maggie Tong from the organisation I work with, Defence Science and Technology Group. Maggie is a recent Sydney University graduate with an honours degree in chemistry and mathematics. She joined Defence Science and Technology Group this year through the Defence Graduate Program and has worked as a future systems analyst in the Weapons and Combat Systems Division. And I've got to say, a very capable new starter in DST from what I've seen of Maggie. So Maggie's going to talk to us about Bayesian analysis to inform technology selections for a multi-agent system. Over to you, Maggie.
Hi, can you hear me?
Yes, I can.
Okay.
And I can see your presentation.
That's good to know. So today I'm going to talk about how you can use Bayesian analysis to inform technology selections for a multi-agent system. So this is sort of a general methodology paper or presentation about a study that we did a few months ago at DST. So first, what do I mean by a multi-agent system? So when I say multi-agent system, what I mean is any sort of modular system where you have different agents that work together to achieve the purpose. So one example of this might be a heterogeneous swarm of unmanned aerial vehicles or drones, where you might have some drones being surveillance drones, some being communications drones. And while each drone might be simple and not be able to do very much, together it uses the power of numbers to achieve a mission. Another example might be a modular fleet of military vehicles, where each vehicle, be it a supply carrier, an armored tank, or a personnel carrier, would have its purpose, but as a fleet, because it has all of these different components which work together, it's able to carry out a range of different missions. So one of the advantages of this sort of modular system is that the developmental costs for each module might be not that high, but together you have this versatility of being able to address a lot of different systems, a lot of different missions. So let's say you're trying to design a modular system from scratch. We'll take the heterogeneous UAV or drone swarm as an example, and you've identified a range of, say, 5 or 10 missions which you want to optimize this system for. Then you have a lot of questions that need to be answered, the forefront of which being, which technology options do I need to build into the agents of my system for them to be able to carry out all the missions that I want them to carry out? Now, if you think of a drone system, then you have lots of technology features that you need to choose. So you need to choose the propulsion system, what material it's made out of, how many rotors does it have, if it has sensors, cameras, and so on and so forth. And each of these components, they don't work independently of each other. How well the overall drone swarm system does against each mission will depend on the interplay of the different technology components. What that means is you don't just need to consider the 10 or 20 or 30 technologies, you need to consider all the combinations. And that number of combinations will grow exponentially. So practically, when it comes to trying to down select which technologies you actually want to include in your system, that's not necessarily an easy problem. So the aim of the problem that we're addressing in this talk is how you can use Bayesian analysis to systematically down select technology mixes and configurations which are most likely to achieve desired mission goals. So we want to figure out which technology choices do we need in our system, and for example, how many different types of drones do I need to achieve achieve the mission purposes. Is 10 drones enough? Or do I need as much as, say, 10 or 20 drones, different types of drones, to achieve a range of different missions? Or can I somehow build some very versatile drones so I only need two or three different types of drone systems? So if we look at the typical engineering process, which one would use to design such a system, you start off with identifying the mission requirements. And sometimes we can do this in the form of developing a series of scenarios which characterize what we want the drones to do. So 5 or 10 stories about how we want the drone to be used to achieve specific purposes. From that, we can generate a range of different concepts, and this is where we explore what sorts of technologies we need. And then from there, we want to down select to a range of different types of drones. So often in this initial step where we have this huge range of technologies, we can't realistically do detailed modeling and simulation of all the millions and millions of combinations of technologies that are out there, because that wouldn't be practical. So what often happens is you do a lot of more, you sort of just pick a few of your best case scenarios which you think might be better based on relatively simple analysis. And then you are left with a smaller subset which you can then do more detailed modeling of to then pick your last few that you want to prototype. So because in practice, it's very hard for you to look at this huge initial problem space, that's a gap in the analytical chain in terms of how you down select the drones. So that's where I think Bayesian analysis can come in useful. We can use Bayesian analysis as a systematic method to take all of the combinations of technologies we're looking at and have a more systematic way of down selecting which technologies that you want to then progress to further analysis and further look at which one you should prototype. So 3 steps to this process. First is constructing your Bayesian influence network, and then populating that Bayesian network before doing some analysis. So for this first step, we are building a Bayesian influence network based on subject matter expert judgment. And the results of this Bayesian influence network need to be dependent on the scenario we're looking at. We need to be able to evaluate each technology mix against every single scenario we want our system to be able to achieve. So we're taking a top-down, bottom-up approach. We need to first look at, okay, so if we want a success metric, so the effectiveness of our system, which are the features that are the most important to our effectiveness metric? So for example, we have these 5 example features of having the required payload, being targeted, durable, having good timing and coordinated. So we've decided that if our swarm system contains the required payload, and that payload might be, for example, if the scenario was to go around and take photos of a particular area, it would need the right cameras, the right surveillance equipment to be able to survey that area. So it would need that required payload. And then it would need to be targeted. So it would need to be taking photos of the correct area that it needs to be targeted. It needs to be durable, so your drone system can't fall out of the air. It needs to be good enough for that. It may or may not need to have good timing to take the photos at the right time. And if it's important in that particular scenario for the drones to work together, for example, in this case, if you have a swarm of drones, you want to survey a wide range of areas. So you need them to be spatially coordinated in order for them to cover the right ground. So we've decided, say, these 5 features are what determine whether our system is effective or not. And from the bottom-up approach, we can look at some technology options. So for example, you might choose a handful of sensors, a handful of navigation systems, different types of drones, and different other payloads that you might want to consider for your technology options. Then with consultation with subject matter experts, we can then build a Bayesian network. Starting from a bottom up, we can see how technology choices can influence different mission level features. For example, how good is it at sensing, how good is it at navigating. And what's important to note is that a lot of these middle level mission features are contextualized to the scenario selected. So you might have your 5 or 10 scenarios, and the sensing requirements for those scenarios might be very different. So for some, it might not matter too much whether you can see very much or not. Others, it might be important. So when we look at the boxes of, is my sensing good enough using this technology, it has to be different depending on which scenario you select. And all of these contextualized mission features need to be able to feed up into the performance metrics, which we've decided determine the effectiveness. So after having constructed this Bayesian influence network, the next step is to populate it with our conditional probabilities and approximations as necessary. So we also went to subject matter experts to populate our Bayesian influence network. So for each node, we asked our subject matter experts the typical questions of, say, if our technology mix has good sensing and good maneuvering for the effect that you want, will it be targeted? What's the probability it will be targeted? And that sort of question to fill out these boxes. So obviously, when you have more than this 3-factor example, then it's not practical to produce the entire conditional probability table manually from the subject matter experts. So we used a linear approximation where we asked the subject matter experts what the maximal probability was, and that was our upper bound, and we filled in we interpolated everything in the middle. And so that practically meant that instead of having to fill out one of these conditional probability tables for each scenario, for the approximation, we would just have to fill this overall one table, so one column per scenario, looking at the contributions. And finally, we asked our subject matter experts for any exceptions and interdependencies. So in some cases, you might have that 2 technologies had to be together or else neither were effective, or that sort of exceptions to the rule, which we then just manually coded into the numbers to have them reflect that. So after having populated the Bayesian influence network, we could then run all of the possible combinations in our QGenie, no, it was Genie, not QGenie, in our Genie model, and pretty much end up with this massive spreadsheet that has all the possible probabilities of each node for each technology mix in each scenario. And what that did was essentially boil down all the different elements of the node into a single number, which is the probability of effectiveness, which we could then use to do further analysis. So the sorts of analysis we could do are, if we look at different technology mix constraints, we can look at best technology choices for individual scenarios, overall scenarios, and we can look at complementary technology choices from when you've already decided some aspects of the system. And what that allows us to do is provide a framework and metric for us to down select our initial wide problem space of many, many, many combinations of technology to a smaller number of technologies that further more detailed analysis can be done to pick what needs to be prototyped in the end. So the sort of data we can get is, we can first just look at the overall spread of data. So this is an example graph, which shows us a few box plots of the spread of data for each of the scenarios. And so the y-axis is the probability at the very top level of node, which is the probability of being effective for that scenario. And just looking at the spread of data can already tell you a lot. So in this example graph, we can see that scenario 1 was a lot easier to achieve than scenario 2. So all the relative effectiveness levels were a lot higher than in scenario 2. So it can tell you maybe our systems, our subject matter experts thought that overall some scenarios were more realistic to be addressed by this drone swarm compared to others. It can also tell you how dependent your systems, so how dependent, how changeable your success is. So if we look at the top whisker, which is the top 25% of the technology mixes. So all of these are for each technology mix, how well did they do? And so this top whisker tells us the best 25% of the tech mixes all did between 80 and 85% well as our metric. And you compare that to, say, scenario 3 in this case, where the whisker is a lot large. And what that would mean is small changes in technology options gives you a very big difference in the relative effectiveness. So looking at this sort of graph can give you an idea of what the differences in the scenarios are and where you might want to focus further efforts and analysis in trying to improve and build your system. Another important thing to note is that technology constraints matter. So the way that our Bayesian network is built is you just have a binary system where either the technology is included or not. And because you have a linear approximation, it means that it will tell you that by definition, the more technologies you include, the better. So without any constraints, our system will just say, just put in all the technologies that will always give you the best results. So we want to give constraints to our system. So we've put 2 sets of constraints. So for example, one configuration might be representative of a system where all of them are the same. So you might have 2 sensors, 2 navigation texts, and just one extra thing, whereas 2 configurations might be representative of having 2 types of drones. And then you can also build some graphs to see how, if the more constraints you put, the worse it does, because less technology gives you less capability. One other thing you can do is you can then obviously rank all of your technology mixes to see which one does best just by the effectiveness matrix, and look at key features. So here for scenario 1, the best mixes all had sensor 1 but didn't have sensor 2 and 3, and you can do the same thing for each scenario to find out which technology is best for each scenario. And what you can also do is down select over multiple scenarios, and that would involve constraining the mixes. And let's say instead of looking at which technologies you want that do best for one particular scenario, we want to cut off everything that doesn't do that well over all the scenarios. And what this does is it finds the jack of all trades of our tech mixes. And then we can filter further and down select further in whatever way you want. So for example, you might just look at which ones do the best overall for looking at the average effectiveness, or you might do some correlation to figure out which ones do well with other scenarios. But either way, what you can do is you can look down select technologies to smaller amounts. What you can then that allows you to find a technology mix that does relatively well over multiple vignettes, and you can compare, say, how well those technologies do compared to the best case scenario. Say in this case, let's say the green line was the best for scenario 1, the red line is the one that we said was the jack of all trades, and it does okay for scenario 1, better for some scenarios, worse for others, and then your blue line is your overall maximum. Another thing you can do is you can say, if you've picked some technology mixes, you can then, some technology options already, then you can just rank everything else to figure out what the best complementary technology options are. So overall, what I've tried to say is we can use Bayesian analysis for this early stage technology scoping option to provide a systematic way to down select technologies to progress to further, more detailed analysis. So some challenges we encountered were that SMA consultations take a lot of time and also are relatively subjective. So the data we get is relatively, they're numbers, but they're qualitative numbers. And also this is an initial stage scoping, so it doesn't consider size, weight, cost, engineering constraints. So that's what further analysis would have to be done for that. Thank you.
Thank you, Maggie. Great presentation. And Anka, questions?
Sure. We have a question from Stephen. How are you choosing priors over your scenarios and selecting the scenarios themselves?
How are we choosing which?
Priors.
Priors as in?
Stephen, would you like to elaborate?
Yep. So you've got the 5 different scenarios there.
Yep.
The example scenarios, at least. So I guess the question's around how were you choosing those scenarios to be, were they intended to be representative of the different deployment situations, obviously, that kind of thing.
Yeah.
And what were the priors? What kind of priors were you choosing over them? And what was the process for choosing those priors?
So in terms of
when you have to, yep, sorry.
So in terms of the scenarios, what would typically, so the particular project we worked on, we had partners and we had a scenario development process, which pretty much involved, so looking at the types of missions that we wanted our system to address. And from there, we had some workshops. So this was done before I got involved in the project, but essentially they looked at the scenarios that we wanted our system to address and had some workshops to develop a storyline, essentially, of this is the sort of mission that we want to address. This is a different type of mission. This is a different type of mission. And essentially, we did workshops to make those vignettes and scenarios up.
Yeah, cool.
And that was, yeah, that was based on what the military priorities were.
Yeah, and so you seem to have quite different results across the different scenarios.
So these were example results. So they're not real numbers, but it was in our real data, we also did have different results because some of the missions were designed to be relatively straightforward and just you had to get your system to this one place and do this one thing, and it was relatively easy and all the numbers would be relatively high and easy to achieve. Whereas some scenarios, so when we're talking about scenarios, we have like a one-line description, maybe our drone system wants to go and take some photos, but then there's like a more detailed storyline of like, so this is in detail the complex scenario that we're looking at. There are all these different elements and this is the bigger picture that needs to achieve. So for some of those storylines, it was a lot more complex and that would make it more difficult to achieve.
Cool. Okay.
Thanks.
And the probability was that?
Thanks. Yeah.
So the probabilities, we had workshops with subject matter experts, explain the model to them and had them around a table pretty much talk. It was pretty much at the top of their heads. So if you have, say, we had some sensor experts come in and we're like, if you have this sensor and this sensor, but not that sensor for the scenario, then which one, what's the probability you think that?
Maggie, if I could just add to that, having worked a little bit on this one, because they were essentially missions, if there was no intervention, the probability of positive outcome on the mission is very, very low, essentially 0. So these are things that are either done or not done. So priors in that sense, the mission scenarios in this case were very much an input into the process, a context.
Yeah.
Any other questions, Anka?
No, not in the chat.
Okay, I'd like to ask Maggie if you went about this process again, you know, just from a clean sheet to, and as I understand the problem, trying to get diverse partners, diverse areas of expertise and diverse technologies grouped together to do this exploration. What have you learned? What would you do differently, do you think?
I think that I would take a lot more time and have a lot more of these consultations. So I think in the actual process, we were sort of doing the consultations to build the model sort of at the same time as trying to elicit data. And that is retrospectively not a good way to do it. We should have had a lot more individual consultations just to finalize the actual model and the network before then trying to populate the data into it.
Yep. No, thanks for that, Maggie. Look, that was a great presentation. You got a lot of information into that short time frame you had. Thank you very much. We're going to move on to our, I think, last speaker for the session, because as I understand it, Anka, there's no sign of Anders, is that right?
That's exactly right.
So we'll be moving on to our last speaker, and Yeah, Maggie, if you could stop sharing your screen. Thank you. So Dennis Shine, a colleague of mine, is an operations analyst who works for DST Group. His research interests include combat simulation, wargaming, and I almost said running, but he actually said running operations research studies on major defense problems. And Dennis is going to speak to us on modeling the force, a Bayesian network approach to support decisions on Army force structure. Over to you, Dennis.
Good morning, everyone. Can you see the presentation?
I can see the screen and I can hear your enchanting voice.
Excellent. So good morning, everyone. My name's Dennis Shine. As Andrew mentioned, I work with him. I also work with Tang, who you heard from earlier, and the other major contributor to this activity was Julia Piotto. So my day job is actually combat simulation, but every now and then we get thrown a woolly problem like this where I can't solve it with my simulation hammer, and I suppose here we are. So this is really all about looking at Army force structure, and I'll explain what that means over the next few slides. So Army is required by government to maintain a certain level of readiness, and this is actually sort of described pretty explicitly by government in terms of you know, for example, you will have to, you know, Army needs to be able to deploy a force of, you know, a certain amount of size, so maybe a company or more, so, you know, 100, 150 people to an austere area, like, you know, say there's a natural disaster in our near region or something like that, and they need to be able to do that within, you know, very stringent time frames, so like, you know, 48 or 72 hours, and sustain themselves, and, you know, it might be a hostile environment. And so because those requirements are so stringent, maintaining the level of readiness to do that is quite difficult. And as such, Army, in terms of the way Army is structured, it's not all ready to do that at the same time. And typically between, you know, sort of a half and a third of the force, depending on the type of force element, is actually ready. And so what Army does is it maintains a force generation cycle or system, depending on how you want to call it. And any particular part of Army, any unit, is either ready, readying, or in reset. So each of those is a phase, and those phases last for 12 months. So ready means that, you know, the force element is ready to be deployed. It's at its highest level of readiness. Everyone is there. No one is allowed to take leave. All the vehicles are working and so forth, and they can deploy within, you know, 48, 72 hours to some crisis. Once they finish ready, they go into reset, and reset is when people take long-term leave, where people go off and do their individual courses. They might break vehicles down for deep maintenance, and so, you know, that's more that you might call it a rest period, but really they're not resting, they're kind of in a different phase. And then after reset is the readying phase, which is where force elements are preparing to be ready. And so they're doing major collective training activities. They're building their competencies so that they are as you know, sharp as they can be to deal with whatever they need to. This whole system was built by an initiative called Plan B Sheba, which is now, you know, sort of about 10 years old, but really you can trace its sort of origins sort of 15 years ago. And that's been our force generation system essentially for the last decade. And Army has decided that that system is no longer fit for purpose and that we need to review how it works. So it's worked quite well for the sort of Iraq, Afghanistan sort of paradigm that we've been in, those sorts of deployments. But the way government is using Army is changing, and I'll explain that a little bit more in the next few slides. So I guess I'll explain the next bit, which is for force generation interfaces with everything within Army. So, and that's why it's such a hard problem to kind of look at. So in interfaces with training, in terms of, you know, depending on what readiness level a unit is at, they'll need different kinds of training, and that training typically you need to book training facilities, align with other units that you want to train with, and so forth. And so if I change the force generation system, I need to think about all of these other factors that are going to get influenced or will influence that change. It also obviously influences operations. So if I change my force generation system, I still need, you know, Army is still on tap to conduct operations and provide forces to operations within within the requirements of government. So any system that I change to needs to still meet all those requirements. The other big influencer is joint integration. So Army doesn't operate alone, and increasingly Army is looking to integrate with the other services, Navy and Air Force, and they maintain their own force generation systems. So they've got to align as best as possible. And if I change my force generation system, I don't want to create some kind of anti-synergy or misalignment such that we miss training opportunities and those opportunities to build those joint competencies. Finally, and quite importantly, and this is one of the key drivers, is modernisation. So in the next 5 years, probably out to 10 years, Army is undergoing a massive recapitalisation program. So we're replacing combat vehicles that are 30 to 50 years old with brand new platforms. The one you see in the picture there is the Boxer, which is a cavalry vehicle that we've recently purchased, and they're sort of starting to come into service now. When you bring a new piece of equipment into service, obviously the soldiers have to learn how to use it. So it's like driving a new car, but also the way they operate or the way they can operate changes. So they've got to rethink all their collective training as well. Typically, when we introduce new equipment into service, we wouldn't necessarily introduce it into the ready force because they need to be at their sort of highest level of readiness, and you don't want them in some kind of transition phase. So if I change my force generation system, I really need to be thinking about where those modernisation points sit, and how Army is going to get all this equipment into service and learn how to use it and change its concepts if necessary, or change its operating concepts. So I've gone over this a little bit. So it's here, to summarize some of the drivers for change. So firstly, there's a change in the demand profile that Army has come under. So you've probably seen, Army being deployed recently for the bushfires and also for the COVID response. And this is quite different to, the sort of usage profile of Army over the last 10 years. So the threshold for government to call upon Army to do things has lowered, and the breadth of requirements of Army has widened. And so that's a challenge that they need to be thinking about. Like I've said, there's this once in a generation force modernisation challenge, so new equipment coming in. The joint force needs are evolving. So, 20 to 30 years ago, joint was, I won't say it, maybe not an afterthought, but it was, a secondary thought to Army just thinking about how it operates on its own. Whereas these days, everything is joint by design. And finally, there's this initiative within Army called the Accelerated Warfare Initiative. And it's really just an acknowledgement that the operating environment is changing extremely rapidly, and Army needs to be able to adapt and evolve more quickly in order to meet those challenges. So the task that we were given for this was to assess future force generation options developed by Army. And so we were essentially tasked to build and apply an assessment framework to understand the strengths and weaknesses of options that have been developed. So this was a pretty challenging task, primarily because we were given a very limited time to complete this assessment. Secondly, the options that we were given were defined in relatively limited detail. So they're still actually under development. And finally, the pandemic influenced us fairly heavily, because typically we would be traveling to various units and setting up workshops and doing things like that. And we essentially had to do the whole thing online, which was quite new for us. So the approach we took was a hybrid Bayesian belief network / utility model using some AHP in there to build the assessment framework. Some of the reasoning there is around, we've got a fair bit of resident expertise and tools in this space, but really it allows a structured elicitation of insights for this problem, which, as you can see, is quite complex. Force generation is a highly interdependent system. I mean, if we had a lot more time, we'd probably still use some Bayesian modeling in there, but we probably would have leaned more heavily on strategic wargaming or some kind of system dynamics model. But essentially, because we were given sort of 3 months for this, we relied more heavily on on what you might call a mile wide, inch deep type of analysis, where we're really just looking to identify the key issues. So we started this work by constructing the assessment framework. So yeah, the classic Bayesian model sort of construction. So what are the important factors? What things are not actually that important that we can kind of put to the side, and how do they all interrelate? Now we've got a lot of expertise within DST, a lot of people who've worked with ARMI for a long time. So we built an initial strawman model, and you can see some of the scribblings down below. I don't expect you to be able to read that. And we took that strawman model to a number of elicitation workshops with about 11 stakeholders across ARMI. So each of those were kind of, 1 to 2 hour workshops where we sort of had various stakeholders help us build out what the key factors are. We finalised this with a review workshop with our sponsor within ARMI. So the conceptual design for the assessment framework is essentially like this. So if we read from bottom to top, we have the options and we have the time horizon as the kind of key inputs. I can't really talk about the options, unfortunately. The time horizon was really thinking around 2 time horizons, one being on implementation, so about 2022. And then the idea is that this will be reviewed in about 5 years. So we thought the second time horizon was actually 2028, so sort of after 5 years. The options then influenced various functions within ARMI. So we have the programs, and the programs within ARMI are all about acquisition and bringing new capability in. So if I change my fourth generation option, for example, I might impact on the delivery schedule of a program either positively or negatively. Then there's the combat brigades and the enabler brigades. So the combat brigades are your basic fighting elements. Your enabler brigades are more specialized capabilities like helicopters and intelligence and health and so forth. And then there's Special Operations Command and 2DIV, are our reserves. So changing the fourth generation system is going to influence each of these things. And then these things then influence on ARMI's ability to do stuff, such as keep costs down, maintain what we would call an appropriate personnel tempo. So a big issue around ARMI is burning out people and having them leave, especially around the enabler brigades, where it might take 10 years to train someone who's an intelligence expert, for example. And then also, the key things around building collective competencies and evolving concepts. And these then lead into our measures of effectiveness, which roughly align around affordability, sustainability, readiness, and modernisation. I won't sort of go into detail here because it's hard to read, but that's the actual assessment framework that we use. So that's the Bayesian model in Gini. The top part there is where we use the utility model, and we actually collected that final sort of level using analytic hierarchy process. So elicitation of the conditional probability tables. So we ended up covering 18 different organisations across ARMI, and this included the combat and enabler brigades, the various training centres, and then elements within ARMI that deal with things such as preparedness and acquisition. Each of those was a workshop of anywhere between 1 and 3 hours. Some of them were done offline, some as well. And they were essentially structured data capture workshops, and where we identified the most relevant nodes for that element. So we didn't ask everyone everything. We kind of picked and choose. But we got some pretty good coverage across the network. So most of those nodes were covered at least twice. Maybe the only ones that weren't covered twice were the acquisition programs, but really there's only one expert in that space.
2 minutes, Dennis.
How long, sir?
2 minutes.
Okay. We use an interpolation approach to reduce the CPT size, which is pretty similar to what Maggie described, so I won't go over that in detail. So some of the results, again, I can't show you any of the results, but we provide a ranking of the options to our sponsor. We identified the critical factors, and we were able to collect plenty of qualitative data around the narrative and the reasoning behind those assessments. In terms of impact, this assessment framework we think is something that's going to be enduring. We don't think necessarily the framework itself will get more complex, but we do want to be able to build more context around that. Some of the tools we use, so there's a DST developed tool that we use heavily called Source, which helps us with our Bayesian network elicitation. It has a number of capabilities in there in terms of being able to mark parents as dependent and independent, and we can do interpolation using that Kane method, has a graphical interface, works directly with Genie. And something we developed just for this activity was a elicitation sheet exporter, which can basically punch out a sheet that you can sort of see down the bottom there. Final slide. So some of the challenges and lessons that we learned. So we were challenged heavily by the compressed study timeframe, and really we would want to do a few different cycles where we sort of revisit results with stakeholders, and we weren't able to do that as much as we wanted. The pandemic was quite interesting. So all our elicitation was either done by Teams, telecon, or offline. So basically, no elicitation sort of face to face. And then finally, it was quite difficult to baseline assumptions, and primarily because the options were limited in detail. So sometimes we were asked questions around assumptions by some of our workshop participants, and we simply didn't have an answer. And so that made it quite difficult to build confidence in some areas. Some of the lessons, and really that's kind of one lesson in 2 points, is around really thinking about those elicitation questions and thinking about the context with which we ask questions. So what does it mean when, if we're doing good or bad in terms of building collective competencies for that particular unit we're talking about? So just sort of wargaming that before we actually go into the data collection activity. And that's it.
Thanks, Dennis. It's good coverage of that. It's a complex issue to go through. And Anka, I'd like to ask you to any questions.
Sure. Jan would like to know if you can explain the elicitation sheet export option in more detail.
Sure. So basically, so source loads a Genie model, and we wrote this sort of, basically the elicitation sheet produces a row for every CPT data point that you've got to collect. So you can see down the bottom there is a pretty simple example where we've got cost of implementation, cost of conduct, and there we're asking the question around low and high, and then the in-between questions there. And we didn't collect percentage, well, we didn't ask for percentages from people. So the scale there, we just looked at sort of a likelihood scale. And what the key thing with it is that you can sort of hit one button, although it's not a button at the moment, but you can hit a button and it can spit out every single question that you need to ask in a sheet. And then we can sort of cut and paste what we need and send that off to a client, and they can fill it in, and it's reasonably intuitive.
Thank you. This were all the questions in the chat.
So Dennis, can I just ask a question then? What would you say about the use of source in this role? Did you have any direct use of source, any experience with it, or was it only via the exported data sheet?
So we use source to actually input all the probabilities in the end. So typically we would use source at DST directly with the person we're collecting the data with, but that wasn't really possible because we did a lot of work over telecom. So source is really something, because it's a hard application at the moment, it's really something where you need to sit down with someone. So we developed the sheet exporter really just for the unique situation we're in right now. The key thing that is really useful for source is that it implements an interpolation method, and it works directly with the Genie format. So once we've input all the information into source, we can go back to Genie, all the data's there, and we can start to look at what the data is actually telling us.
So just on that, given the use of source, and one of the strengths of source, I think, is that you can rapidly shift between a independent of causal inference parent to a non-dependent or independent. So I'm wondering how much that was used, or how many dependent parents did you end up with in doing your elicitation? Was it a big issue is what I'm trying to say.
Oh, sorry. Yeah, so there was a mix of dependent and independent parents. Primarily the dependents were marked for the fourth generation input, and the two input nodes, fourth generation option and the time horizon. So that's where we had to, that's where we couldn't use any interpolation. We had to ask those as direct questions.
But there was no, I'm assuming there was no need during elicitation to shift between a dependent and independent?
I think if we had more time, we might have looked at some of them, because like, and the example there is actually on the screen I shared, which is there is a little bit of interdependency between those various collective competencies, which if we were doing this a little bit better, we might have started to look at that. But in the case of this study, we didn't. But you can do that, I guess, is the.
Yeah, okay. No, thank you very much, Dennis. And we will now move on to the final part of this session. If you could, thank you very much. And screen sharing. So we have 10 minutes left. And what I'd like to do first is, if there are any remaining questions on any of the speakers who are still with us, we'd like to take them and give an opportunity to have that burning question that you didn't ask. If we get through that, or if there are no questions, then Marek has kindly agreed to do more of a demo and possibly answer more questions on QGenie. So first of all, are there any further questions on any of the speakers in this session?
So at the moment, there's nothing in chat, and until something appears there, I would just like to make a comment rather than a question for both the presentations that we just had from Dennis and possibly from Maggie. Maggie introduced an interesting concept of qualitative data, referring to the data elicited from experts. And my comment would be that that data gets more and more quantitative if the expert elicitation is a bit more structured and the answers are aggregated from more than one expert. And I understand that from Dennis that sometimes there's only one expert, or there's a perception that there's only one expert. So if we relax a little bit the definition of an expert, and we allow more opinions to be given and then aggregated, the data becomes more quantitative, as a way.
Thank you. So if there are...
There's a question for Marek from Tang.
So maybe what I would ask first is, Marek, if you're still online, I think you are, would you like to then start screen sharing and be prepared to address the remainder of this session? Thank you.
Okay, so I have a question for Tang, but before that, I think we had a question from Helen that we didn't have time for, and she was asking, can you easily convert a parameterized Gini model to a QGenie?
Unfortunately not. This is a one-way conversion. The reason for that is that Gini doesn't know De Morgan. You know, one day in the long run, we may implement De Morgan in Gini. Then the conversion can be possible. But at the moment, it's just one way from QGenie to Genie.
Marek, can I just add to that? I think in one session I was talking with you, you showed me how to go from a QGenie model into a Genie model, make a change, and then because I haven't really modified the structure, you showed me a way to get back into a QGenie format, fairly straightforward, but not directly from a straight Genie model, I guess.
Yeah, I would like to put a little bit on, because I read Marek's paper and I read the master student and put a lot of detail how to calculate from De Morgan into CPT. So it means that you go from a small, so you can go that way, but you to reverse it back. It's quite mathematical challenge, probably need to work, and you need to do some approximation into that one. So that part it needs to address mathematically before Marek can do your reverse back. Is it right, Marek?
Reversing back is a problem because
okay.
Well, if we had De Morgan in Genie, we would just translate it directly into De Morgan. But what we do is we just produce CPTs. So if you look at this model in Genie, it's just CPTs. So it's not going to work too well. Although, I don't know what I showed you, Andrew, but these 4 influences are just positive influences on the child. So they are noisy or pretty much. So if you go back to Gini and you have a CPT, one thing you could do is you could fit to it noisy or distribution, just changing the type. And this is probably the same as what you see in QGenie, I think. 0.4, 0.6, 0.6, 0.3,
Yes.
and 0 leak. Is this what we see here? The leak is 0 indeed, and we have 0.4, 0.6, 0.6, and 0.3, right? Yeah. What you could do is probably make sure that a node has the same type of influences, and then you could interpret these nodes as noisy or which are known in Genie. So
yes. Yeah, I think there was definitely constraints on what you showed me, but there was a specific situation we could do, go QGenie to Genie, make a very small change, bring it back into Genie. But yeah, there were all those constraints that you mentioned.
There are no special facilities for elicitation of numbers. I noticed several of the speakers were concerned, and rightly so, concerned with elicitation of numbers. Here we just assume that it's direct elicitation. So you know, you go there and you you slide it to get that number. So nothing complicated. Of course, you could apply a complex elicitation technique to any of these numbers outside.
Yeah, Marek, sorry, are there any other questions, Anka, before I start asking more questions?
Tang posted a question for Marek about or, and negation and QGenie. I'm not sure if you want to elaborate, Tang.
Yes, because there are 4 definitions of node in QGenie. And I understand that Marek tried to converse between noisy or, noisy max, and negation to those ones. So I would like to hear more on explanation what is relationship between those ones.
Between these 4 different types. So
yeah,
I would think that you know, these are simple because most of you probably know noisy or, right? So positive influence. This node, when it's true, it influences. Oops, sorry. When it's true, it has positive influence on the child. Now, this is it's a barrier, I think we call it. It's a barrier.
Yeah,
it's a negative influence. So essentially, negation, it's just a matter of reversing the states. You can't do that in QGenie, but in Genie you can easily reverse the state of states. So you go to, let's say, this one, you can go there, and you reverse the states, and that is pretty much negation. Now the problem is with reversing the states, it will not always work because a node may be parent to 2 different nodes, and it may influence this one positively and this one negatively. So you actually need negation as a tool. Of course, you could organize it by having an intermediate node that just negates that can be also done. So this is also quite easy because it's just negation, right? So let's put it on the side. Now these 3, these are the ones that are interacting like AND nodes. So the aspirin intake is an AND with fever, and Tylenol intake is also an AND. By the Morgan laws, AND is there is this formula. Let me open the Genie Health because the formula is there in the building blocks. I think Isn't it here? No. Okay, here it is. In the Morgan gate, here is the, I think I can make it larger. Here is the formula that is being used in the gate. We have OR, so this is actually noisy OR, C1 and C2. Now this is noisy OR with negation, so you negate, reverse the states, and then you have an OR also. And the requirements and inhibitors work as AND together. So you could construct a model easily that is an AND. Let me do it quickly. So we have 1, 2, 3 nodes and a child. If you use only the requirements, then you get an AND gate. This is an AND, essentially. Any of these, all of these have to happen for the child to happen. Let me just put some non-zero influence, whatever it is, and this thing will behave like an AND. Leak, let's make it, well, the leak in AND has to be large, I think, if I remember. So now, if I make them visible as bar charts, you can see what is happening. One of them being, one of them being true will not change much the result. 2 of them being true will make it bigger, but 3 of them being true will make it the biggest. So it's really working like an AND. One of them false brings that probability of the child very low. It is an AND gate. So the requirements are essentially an AND gate. And this necessary condition is actually, this is the requirement. These things are, they are called inhibitors. They are essentially negated nodes. So it's an AND with negated values, reverse values. So at some level, it's intuitive. What is difficult? There is a difficulty in this use of QGenie, and it's very easy to get confused here. I'm getting confused myself sometimes. And another thing that happened, even in the paper, the original paper with Maskant, even his thesis, there are errors. Essentially, we got confused in asking questions. What kind of questions you need to ask? Here are the examples of questions, and QGenie Online Help is actually the most up-to-date, and it's correct. I'm fairly convinced it's correct. So
Marek, I'll have to
interrupt.
Give you 1 minute to finish off what you're just talking about now, but then we'll have to end the session.
You know, the difficult thing is really the questions that you ask. What kind of states do the other nodes have to take? And that depends on whether it's the AND or an OR node. OR node has to be in the distinguished state. The AND nodes also, I think, but the distinguished states are different. Anyway, this is a confusing thing. You need to become proficient to stop making errors here when you build practical models. When there are multiple types of nodes coming into a child. Okay, I'm stopping here.
Yeah, thank you very much.
Hey, thank you very much, Marek, and thank you for all speakers in this session. Much appreciated. Really enjoyed all of the talks. I think certainly from the DSTGN, I'm sure we'll be willing to take any questions from anyone who's interested at the level at which we can speak about the work, and maybe there are some tools that we can even investigate sharing if there's of interest. Certainly collaboration would be great. But I'd like to thank everyone who participated, and I'd like to hand back now to Anchor before I get stood on by a morning coffee crowd.